In this video, I'm just going to get right down to it. We're going to do 3 examples to find the real zeros of a polynomial. In example 1, we want to find the real zeros of this cubic polynomial. And so the first thing that I recommend doing is listing all of the potential real or potential rational zeros using the rational zeros theorem. Remember, in order to do that, we take the factors of p, the constant, divided by the factors of q, the lead coefficient. In this case, p is, all the p values would be plus or minus 1 and plus or minus 7. Our q values out front are just 1, plus or minus 1. So listing all of the potential rational roots, we have 1 over 1 and 7 over 1. So it's plus or minus 1 and plus or minus 7. The next thing that we can use is Descartes' rule of signs. The reason that I just don't want to go about testing these is I want to maybe see, is Descartes' rule of signs going to tell me if I definitely have a positive or a negative? And it's pretty easy to see and use. In order to use this, we first see how many sign changes we have in regular f of x, and that's our capital P, not to be confused with the lowercase p. I'll make it look different. This capital P means positive. So we do have a sign change from here to here, positive to negative, that's 1. We have another sign change from here to here, and a third sign change from here to here. So our possible, the number of positive real roots could either be 3 or 1, since we had 3 sign changes in f of x, and then we can go down by 2. Then we want to find f of negative x, and that'll help us find how many negative zeros that we could have. So f of negative x would look like negative x cubed minus 7x squared minus x minus 7. And we actually do not have any sign changes in that. So our n, the number of negative real zeros that we have, is none. That means that we're not even going to test out the -1 possibility or the -7 possibility. So that's how Descartes' rule of signs can help us. Now we're going to actually test to see if +1 or +7 is a potential real zero. And I realize I said potential, I just mean is an actual zero. The way we're going to do that is through synthetic division, unless you really want to do long division, but I doubt it. So the first one that we're going to test out is the +1, because we're told that we could have either 3 positive real zeros or 1 and no negative real zeros. So no need to test -1 or -7, those potential rational zeros. Let's test and see if x equals 1 is a real root. That means we're going to put 1 in the corner and do synthetic division. So we use all of our coefficients, 1, -7, 1, and -7. We do not have any missing terms here, so we don't need to put in any zero placeholders. Remember, a number is a zero. It's a root if we get a remainder of 0. That means it fit in perfectly. So we'll do our synthetic division, bring down the 1 times 1, add those, multiply -6 times 1 to get -6, add 1 and -6 to get -5, multiply -5 and 1 to get -5, and we have a remainder of -12. Because we have this remainder, because our remainder is not equal to 0, that means that x equals 1 is not a root or a 0. It didn't work. So the next thing we have to do, we'll test 7. We'll see if 7 is a root. So we put 7 in our corner and we do synthetic division again. So we have 1, -7, 1, and -7. And we do our synthetic division. Bring down our 1. 1 times 7 is 7. We add -7 and 7 to get 0. 0 times 7 is 0. 1 plus 0 is 1. 1 times 7 is 7, and we have a remainder of 0. So because the remainder equals 0, x equals 7 is a root. Now, according to the fundamental theorem of algebra, what did that tell us? Our fundamental theorem of algebra. Our degree of our original function is 3. So that means we have 3 total roots. Well, roots can either be real or imaginary, and in this chapter we only care about the real ones. So that means that all three of these roots could be real. We definitely know that 7 is one of them. 7 is one of them. We found that here using synthetic division. However, might we have 2 more real roots? The way to do that is to see what remains from our synthetic division. What remained was this quotient here. It was 1x squared plus 1. That was our remaining quotient. So we want to see if we can take x squared plus 1 and see if we have any more real roots to that. Well, we could do a couple things. We could see if it's factorable. It's not. We could use the quadratic formula on it, which I will do, or we could just straight up solve it. I'm going to use the quadratic formula on this. When doing the quadratic formula, we want to identify a, b, and c. A is 1, b is 0 here because we don't have an x term, and c is 1. So we'll have the opposite of b, plus or minus the square root of b squared minus 4 times a times c all over 2 times a, which gives us 0 plus or minus the square root of negative 4 all over 2. Because we have a negative under the root, that means that we have imaginary solutions. Our discriminant is negative. We do not have real solutions to this quadratic. So these are imaginary roots or solutions. That means that the final 2 roots out of the 3 total ones for our cubic are imaginary. The only real root is 7. Now, I know this seems like a lot in one example. Let's go over what we did. We started off by listing all of the potential rational roots using the rational zeros theorem. That is what your first step should be. Use the rational zeros theorem to list all of those possible rational zeros. The next step that you should do is to use Descartes' rule of signs. This tells you how many potential positive and negative roots you have. We found using Descartes' rule of signs that we didn't have any negative roots. That's why I didn't have to test -1 or -7. I knew they wouldn't work. I also found out from Descartes' rule of signs that we either were going to have 1 or 3 positive real roots. That means I could feasibly test the positive ones here that I got, and I did. That's the next step. We tested those roots that could potentially work. We tested them using synthetic division. So test your possible roots that might work. If you get 0 as a remainder, that means you had something that worked. It fit in perfectly. You didn't have any remainder. So that meant that 1 didn't work, but 7 did. Once you have gotten down to a remaining quadratic, we know how to deal with quadratics. We can use the quadratic formula on them, meaning once you are down to your quadratic through synthetic division, you should use the quadratic formula. Your quadratic formula will tell you whether or not you have real roots remaining or imaginary ones based on if you have a positive or negative under your square root. If you have a negative as the discriminant, they're imaginary, and we don't need to worry about them. Lastly, what I did was, and that was step 4, quadratic formula once you're down to a quadratic. The other thing that we talked about throughout this process was the fundamental theorem of algebra. This tells us how many total roots we should have. Because it was a quadratic, we know that we had 3 total roots. However, only one of them ended up being real. So our final answer was just 7. Here's our second example. We again want to find the real roots of this cubic polynomial. Our first step is going to be to use the rational zeros theorem to list just those potential rational zeros. We do this by finding lowercase p, all the factors of 6 are constant. The factors of 6 are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Q is all the factors of our lead coefficient. In this case, it's 1. So since Q is 1, when we put all of our p's over q's, which is what this theorem tells us to do, we're just putting these numbers over 1. That means, really, all the potential rational zeros are just the p's. because putting them over 1 is not changing anything. So we have 8 potential rational zeros, 4 positive and 4 negative, because q ended up being 1. So that makes it a little bit easier. Now, because we have half of them negative and half of them positive, I'm going to use Descartes' rule of signs to kind of determine maybe where to start checking. Descartes' rule of signs is going to help us know how many positive or potential, how many negative roots we're going to have. So we want to first count the number of sign changes in just regular old f of x. We go from a positive to a negative, that's 1. Negative to negative, that's not 1. And then a negative to a positive. That means that our potential number of positive real roots, or 0, I'll use zeros since we said that before, is either 2 or 0, because we can go down by 2's. Then the number of negative real zeros is determined by a little bit more work. We need to find f of negative x. F of negative x is going to be negative x cubed, because it'll change the sign of that term since it has an odd exponent. It won't change the sign of this next term because it's an even exponent. It will change the sign of 5x because that's an odd exponent of 1. And it won't change the constant because that constant's not affected by x at all, or negative x. Now we count how many sign changes we have. None here, and then 1 here, and none here. So that means we have to have 1 negative real 0. All right, well, that's not super helpful, because that means that since we're going to have one negative real 0 and we could potentially have positive real zeros, I guess it sort of helps us because we know we have to have a negative real 0 where we definitely don't have to have a positive real 0. So I'm going to start by checking the negative possibilities from here. -1, -2, -3, and -6 with synthetic division. The first negative value I'm going to test is -1. That seems the easiest. So we're going to do synthetic division with x cubed minus 2x squared minus 5x plus 6. There's no missing terms, so we can just list the coefficients with no placeholder zeros and perform our synthetic division. Bring down the 1. 1 times -1 is -1, and then add. -3 times -1 is 3, and then add. -2 times -1 is 2. And then we'll get an 8 as our remainder. That means that -1 didn't work because we got a remainder that wasn't 0. The next negative real root I'm going to test is -2. We're going to do the same process. So doing synthetic division here, we multiply and then add vertically. We multiply again and then add vertically. 3 times -2 is -6, and voila, we get a remainder of 0. That means that x equals -2 is a 0, or a root. This polynomial hits the x-axis at -2. So that accounts for our negative real 0. We know we don't have any more negative real zeros because there's only 1. So now what do we have remaining? We have a quadratic remaining since we took a cubic and we performed synthetic division on it. It knocked it down to a quadratic. Our quadratic is 1x squared minus 4x plus 3. That's going to be our next step, is finding the zeros of that quadratic using the quadratic formula. So we have this remaining quadratic. When you have your remaining quadratic, it is x squared minus 4x plus 3, and I'm going to set it equal to 0 to solve it. Now, we have solved quadratics by factoring and using the quadratic formula. This is actually factorable. I'm going to do it both ways. There are two numbers that multiply to 3 that add to -4, and those are -1 and -3. When we set both of those to 0, we'll get that x equals 1 and x equals 3. You can also use the quadratic formula if factoring is a bit much for you. So using the quadratic formula, so this is an or, you can solve by factoring or the quadratic formula. Here's our quadratic. A is 1, B is -4, and C is 3. We take the opposite of B, plus or minus the square root of B squared minus 4 times A times C all over 2. So we get 4 plus or minus 16 minus 12. Under here is 4. The square root of 4 is 2. Then our plus gives us 4 plus 2, which is 6 over 2, so that gives us 3. Our 4 minus 2 is 2, and 2 over 2 is 1. So it gives us the other two answers of 1 and 3 either way. So it's completely up to you. If it's factorable, feel free to factor. And if it's not factorable, or even if it is, the quadratic formula never fails. Here's what we've found. Here's our final answer. Due to the, not due to, but because the fundamental theorem of algebra tells us that a cubic, degree 3, has 3 roots, we found that all 3 of those roots happen to be real. We found that -2 was one of our roots, and we also found that 1 and 3 were the other 2. So our 3 real roots are x equals -2, 1, and 3. Let's graph this to see if it works. Okay, we can see in here that we definitely have 3 real roots, and they do occur at x equals -2, x equals 1, and x equals 3. So that is what we found algebraically. Why couldn't we have just graphed this from the start? It's pretty cool that we can. We've come from abacuses, like I work with a coworker who's in his 60s, and he said we are so lucky now to have the technology that we have. Definitely if you have very simple roots that are integers, for sure you can just graph it and see. However, when you have some more complex ones or imaginary ones, we need the algebra and not just the visual entity of the graph to find those. However, graphing is a great tool to check your algebraic work. This last example is not really an example, it's a you try. So what I'd like you to do, I didn't write the directions, whoops, find all the real zeros of this cubic and go ahead and pause, and once you're ready, hit play to see how you did. Here is the work. The solutions are -6, it occurred once, so it has a multiplicity of 1, and x equals 1 occurred twice, it had a multiplicity of 2. So the fundamental theorem of algebra tells us we have 3 roots. They happen to all be real, and here they are. This one occurs twice, so it counts twice. The rational zeros theorem gave us these potential zeros. Q was 1 here, so we just had to list the factors of 6. Descartes' rule of signs told us that we had either 0 or 2 positive real roots. Turned out it was 2. And 1 negative real root, which was -6. So I definitely tested all the negatives because we for sure had one of them. So I tested all of them, and then -6 ended up working out, gave us a remainder of 0. If you note here, I didn't even want to do 14 times 3 because I knew it wouldn't work to give us a remainder of 0. All right, once -6 worked, we knew that -6 was a root. We were left with a quadratic because we started with a cubic. And this quadratic was actually factorable. It factored into x minus 1 times x minus 1. Solving that gave us x equals 1 2 times, so it had a multiplicity of 2. You definitely could have used the quadratic formula, but when it's factorable, there's no need to do so. All right, I know that's a lot, but hopefully going kind of in this order allows you to find some semblance of an order to how to find the real zeros of a polynomial.